In our previous chapters dealing with thermal physics, we looked at the properties of ideal gases to try and understand the variables that affect the state of the gas, such as pressure and volume and temperature and the amount of material. From that, you recall, we developed the ideal gas law, which allowed us to relate those macroscopic quantities. We developed the kinetic theory of gases, which enabled us to connect up a microscopic picture of the gas as comprised of atoms to the macroscopic state of the gas as expressed in the ideal gas law. And then we went on and we looked at some properties of materials relating to the way they absorb heat energy and how their temperature changes or their phases change. We introduced the concept of specific heat and latent heat. And we also looked at the mechanism of heat transfer. So notice that all of these topic areas are dealing with the idea that heat as a form of energy is being placed into or taken away from a substance, and the response of that system to that change in heat energy is expressed through temperature changes and gives us specific heat and latent heat. Oh, okay. Very good. Now we want to bring this all together under the area of thermodynamics. The connection between thermodynamics and the previous chapters in thermal physics is the same connection that we used when we went from kinematics and mechanics to dynamics. Recall that kinematics was a description of the mechanical motion, and dynamics connected that up to the causes for that motion. Well, in the same way, thermodynamics looks at the causes of the thermal phenomena, just as the prior chapters dealt only with the description of what was going on, the description of the state, the pressure, the volume, the temperature, the description of the heat transfer. Now we want to take a look at the thermodynamic system and say, what is causing the system to do work for us as a result of the energy that is put into the system, and then how has the energy of the system itself changed as a result of these processes occurring. And essentially, this is conservation of energy. Now, we will develop other thermodynamic concepts, but we're really looking at taking that idea of the conservation of energy now and applying it to a thermal system. First of all, we need to define some units here, and prior to the middle 1800s, one of the prevalent theories that existed discussing heat and temperature was known as the caloric theory, and the calorie unit arose out of the caloric theory, and this was a unit of heat. And it wasn't properly understood that heat was actually a form of energy until James Joule performed an experiment that showed that mechanical work being done by a system that was rotating some paddles inside a bucket of water, essentially. The paddles were rotating as a result of some masses that were falling on a pulley system, and those falling masses represented mechanical work, which could be calculated, obviously, from potential energy being mgy. And then Joule measured the small temperature increase of the liquid as a result of the mechanical work done by the paddles moving in the water, and measured the temperature change and calculated the amount of calories that would be necessary for that temperature change. And Joule was able to show that 1 calorie of heat was equivalent to 4.184 joules of mechanical energy. And this concept became known as the mechanical equivalent of heat. And it set the connection between mechanical energy and heat energy. In other words, heat is just another form of energy. And so you can use this equation, or this relationship, that 1 calorie is equivalent to 4.184 joules of mechanical work. So in terms of energy then, energy that we have studied up to this point, kinetic energy, potential energy, kinetic energy in the form 1/2 mv squared for linear kinetic energy, as well as rotational 1/2 I omega squared. Potential energy, of course, takes the form dependent upon the force law. For instance, the potential energy associated with the gravitational force being mg times the height y above your reference level, or the potential energy of a spring, 1/2 kx squared. So you notice that those are different forms for the potential energy because the force law is different for each one. And then, of course, the total mechanical energy E is the combination of kinetic plus potential energy. Recall that we can do work as a result of the presence of energy, that energy is transferred. So that is evidence of the existence of energy, is that the system can do work. And therefore, since heat energy put into a system can do work in the form of expansion of gas, then we know that heat is just a form of energy. So we're going to need to take the conservation of energy principle and expand on it a little bit in order to accommodate these new thermal terms. Now, first of all, let's take a look at our typical system that we will be using as our ideal thermodynamic system. And you notice what we have here is a cylinder which contains a gas, a very dilute gas, and a piston. And this system can be characterized by the state variables, pressure, volume, temperature, and the number of moles. And as you know, since it has those variables, we can use the ideal gas law, which describes the relationship between these. Recall that that's PV equals nRT. So this is our ideal system, and we want to study behavior of the system under the influence of external forces being applied to it, to the piston, or heat being added or taken away from it, and see how the system responds. So one question would be to ask is, what happens to the gas if the piston is moved inward? Okay, what definite things can you say happens to the gas? Well, you can definitely say the gas's volume has decreased, can't you? Some might say, well, the temperature is going to go up. And the answer to that is maybe. You don't know that for sure because you don't know whether or not, as a result of the piston being moved in, and which could result in the temperature increase, but that heat energy might flow out through the walls of the cylinder, or the piston cylinder arrangement may be in an environment where there's sufficient heat capacity to absorb all that heat energy and maintain the temperature inside at the same temperature. So, of the things you can definitely say about this, in this situation, that the volume has definitely decreased, hasn't it? Now, if we put this container in an insulated environment so that there is no transfer of heat energy to the outside, then we can say the temperature will definitely rise because there's nowhere for it to go to conduct through the walls. And as a result of the temperature rising, the kinetic theory of gases, recall, tells us that the temperature of the gas is directly related to the kinetic energy of the gas. Therefore, at a higher temperature, the atoms have higher kinetic energy and move faster. If they move faster, they strike the walls more often, And each time they strike a wall, remember the development of the kinetic theory of gases, we looked at the collision of particles with the walls and the force those particles exerted on the walls as a result of those collisions led to the pressure. So if they're colliding with the walls more often and they're moving faster, the pressure is going to rise and the temperature is going to rise. Now, is there more internal energy in the gas? Well, recall what internal energy was. Internal energy for an ideal gas is the kinetic energy of each of the constituents of the gas all added together. And since kinetic energy was the only energy that we were allowing based on our assumptions that these particles are very far apart, they collide very rarely with each other, they are elastic, and they don't stick together in the process of collision. Therefore, the only energy they possess is linear kinetic energy, and therefore the total internal energy is the sum of all the kinetic energy of the individual particles. So if the temperature rises, then there's more kinetic energy, therefore the internal energy is greater. Now, this is a conservation of energy process, so recall that in conservation of energy, you have to ask the question, where's this energy coming from? In other words, if the temperature rises and the internal energy increases, it had to come from somewhere. And it comes from the fact that the piston being pushed inward is being acted upon by an external agent, which exerts a force on that piston to move it downward through a distance shown here by delta x. And that force, based on the definition that pressure is force per unit area, we can rearrange that and express force as pressure times area. We see we have an expression here that says that the work done is equal to the pressure times the change in volume. Now, notice that the change in volume, if you compress, go from a larger volume to a smaller volume, the change in volume is going to be a negative number. So that's going to represent the energy lost by the agent doing the work, a negative number. Contrary to that, that is also going to represent the energy gained by the gas. Okay? So P delta V, if the gas is being compressed by an outside force, that means that amount of energy is going into the gas. So the gas is going to increase its energy content as a result of the external agent doing work on it. Work done on the gas equals the change in internal energy, in this case. Okay? Notice there are no other factors involved here. We aren't adding heat to the system from the outside. We're just saying, what if an external entity comes along, pushes that piston in, does work on the gas, where does that energy go? And if the piston and cylinder are insulated from the outside, that energy can't escape through the walls. Therefore, it must simply remain within the gas in the form of increased internal energy. So this is one option. That is that when you do work on a gas, you change its internal energy. Okay? And we want to take into consideration all possible scenarios, and this is only one scenario, that when you do work on, you make its temperature go up, and that as a result changes its internal energy. Let's change the situation, and let's keep the piston fixed in its original position. You can imagine, say, welding the piston to the walls of the cylinder. And placing this piston and cylinder arrangement on a hot plate or a stove or some source of constant heat energy. Okay? And then what happens to the gas in this circumstance? well, I don't recommend you try this, but of course what happens is that as the heat flows in to the container, now it's not insulated at the bottom, the temperature of the gas rises, the pressure rises, and ultimately we might reach some critical point. But notice that the piston being fixed in place is not able to move, it's not able to expand the gas, so no work is done. Remember that work is pressure times the change in volume. If the piston is fixed in place, the volume can't change. So no work is done. The gas doesn't do any work pushing outward. So the heat energy that goes in, that symbol is Q, then goes into the gas and is reflected as a change in internal energy, which we know happens because the temperature rises. And the pressure, of course, increases even though the volume doesn't. So we see heat put into the gas equals the change in internal energy. Remember before when we had the gas being worked on by an outside agent, that work changed the internal energy. Now we have heat coming in, changing the internal energy. So we have two parts of the puzzle. So we could do both of these things at the same time. We could have an external agent push the piston down and compress it. At the same time, we could have the cylinder residing on a hot plate, and these two effects having at the same time would then result in the internal energy, the heat, and work being done simultaneously. In such case, notice that we have a relationship here that is a conservation of energy relationship for all of these possible circumstances. And it essentially says this. It says the heat that you put in is or can be apportioned between two possible outcomes. One is the system can do work, and the other is the system can have its internal energy changed. So those are the two consequences of adding heat to a thermodynamic system. So let's say that again now. Q is the heat. Then let's say you are putting it in because you're adding heat to your gas in this cylinder. Now, if the piston can move, the gas may expand outward and do work, and that would be one reflection of the heat energy added to it. So that's what the W there is there for. Also, the gas may increase its temperature while this process is occurring, and therefore its internal energy is changing. So there's another consequence of adding heat. So we have those two possibilities. This is known as the first law of thermodynamics, and really it's just a conservation of energy statement about what happens when you add heat to a thermal system. That system can do work and have its internal energy altered, both or neither. Now we do have to pay attention to the positive and negative signs that are associated with the terms in the first law of thermodynamics. I prefer that you think about the process first before you start trying to apply conventions to equations. In other words, you know that if you add heat to a system, let's call that positive energy, you've added energy to it. So that seems quite obvious that that's going to be a positive sign for heat flowing in and a negative sign for Q for heat flowing out. Now what about the work? Well, ask yourself a question. Who's doing the work? If the gas is expanding, and therefore the gas is doing the work, then the gas is expending energy in the process of this expansion. Its energy must decrease. So if the gas is expanding and giving up energy in the process of doing that, its the sign of that must be negative to the gas. Now, to someone on the outside to which the work is being done on, in other words, if you have a weight, a mass sitting on the piston, and the piston is being pushed upward, and that mass increases its potential energy, then the work being done on it is positive. So look at the perspective of who are you talking about? Is the gas gaining or losing energy as a result of the work? And if the gas is doing the work, it must lose the energy. If work is being done on the gas by an external agent, then the gas is gaining that energy. Okay? So work done on a gas is positive because someone is external to the gas is doing work on it and adding that energy to the gas. Work being done by the gas is negative. Those two words are very important. On and by. If work is done on me, then I gain whatever that work is. If I am doing work, I lose whatever work that is. And of course, if temperature goes up, the internal energy increases. Temperature goes down, the internal energy decreases. So positive change in internal energy with increasing temperature, negative change in internal energy with decreasing temperature. So before you try and apply the first law of thermodynamics without consideration of these concepts, just look at the problem you're dealing with and ask yourself, is heat flowing in or out? Who's doing the work? And is there a temperature increase or decrease? And then that'll tell you what the signs are for these terms. Well, here we have an example. We have 25 liters of gas enclosed in a piston cylinder arrangement at 2 atmospheres of pressure and 300 Kelvin. Now, before you even go on, just think about that for a second. We should label what we know here. We have a volume, 25 liters. If you divide that by 1,000 liters per cubic meter, then that's 0.025 cubic meters of volume. We know the pressure of 2 atmospheres. We need to convert that to Pascal units by multiplying by 101,300 newtons per square meter. And of course, the temperature is properly expressed in Kelvin. So we have the pressure, volume, and temperature of one state of this gas. We have a 100 kilogram mass, which is placed on the piston, which then causes that piston to move inward and compress now to 20 liters. So we have an external force, the weight of the object due to gravity, acting to do work on the gas. And this compression has been at constant pressure. Now, if it's done at constant pressure, that means the pressure didn't increase as a result of this compression or decrease in volume. Does that seem right to you? What would have to happen in order for the pressure not to go up? That's right. Since an external force is acting on the gas, doing work on it, you would expect that work to be reflected as an increase in the energy of the gas and to be reflected as an increase potentially in pressure and temperature. But the pressure doesn't go up, so it must be that we're allowing some of this buildup of heat energy to flow out of the system. And as I say, this is done by allowing heat to flow out of the gas. So what is the work done on the gas? Well, the definition of work is pressure times change in volume. And we have a volume going from 25 to 20, a negative change in volume of 0.05 cubic cubic meters, and a pressure of 202,600 pascals. So we can calculate the work. What is the change in internal energy of the gas? Well, do we know the temperature change? Well, we know the pressure is constant. We know the volume changed. We can use our ideal gas law to calculate the temperature at the new conditions of twice the pressure and 5 liters of less volume. I'm sorry, same pressure and 5 liters of less volume. So use PV equals nRT to find the new temperature and see whether there's a change in temperature and therefore whether there's a change in internal energy. And then once you know the work and the internal energy, and you know whether or not those terms are positive and negative, you can add them together and find out how much heat had to flow out of the gas. Well, that's the verbal description of what's going on. Let's take a look at the calculation. Notice we've listed all of the initial conditions as well as the final conditions. And we need to calculate the temperature, the final temperature T sub F, using the ideal gas law. Also, we've listed the equations we're going to use, the ideal gas law, the definition of work, the change in internal energy, as well as the first